Our next speaker is Perry Stevenson, a senior software engineer at Atlassian. He will describe how he uses the Databricks platform to develop forecasting models for ticket volumes for different groups within Atlassian. Please welcome Perry.
Hi, my name's Perry and I'm a software engineer at Atlassian. Today I'm going to talk to you about how I was able to use the Databricks platform to build an automatic forecasting pipeline that was robust, fault-tolerant, auditable, and reproducible. I'm speaking today because I'm one of those empowered end users that Databricks serves so well. The platform gave me everything that I needed to build all of this pipeline without any help from engineering. I'm also speaking because I've spent a lot of time thinking about reproducibility, and I've got some opinions about how the Databricks platform can make your projects a lot more reproducible. And finally, I love working with Databricks. What can I say? So, a little bit of a caveat before we start. I'm real, this is a real project, and that means that it's messy. But hopefully, you'll get some useful ideas and inspiration. And typically, we would pause here for a moment to talk about how this project fits into our business and what we're trying to achieve. But we only have 15 minutes, that's just not happening. All you need to know is that we're trying to forecast support ticket volumes across a bunch of different ticket groupings. What you do need to know is that forecasting is a special case for machine learning. Forecasting models are short-lived, they're ephemeral. It's the pipeline that matters because you need to retrain every time you make a prediction. And what that means is that we don't get to take engineering shortcuts when training models. We need to ensure that the whole pipeline is robust and maintainable. Looking at it another way, the process looks like this. We do some one-off modeling dataset creation tasks, but then we schedule the update of the modeling dataset, we schedule the model training, and we schedule the scoring. It's a subtle difference compared to normal machine learning workflows, but it's an important one. And that brings me to the agenda for this talk, where we're going to dig into the technologies that make this work. We'll start by talking about Delta Lake, which is the tool we're using for the modeling dataset and also for the model outputs. Then we'll take a look at MLflow tracking, which is how we're managing the fleet of models needed to generate the forecasts. Then we'll look at notebook workflows, where we've taken an imperfect process and made it robust and reproducible by using notebooks. And finally, we'll review the pipeline to see how well it's achieved its objectives. So let's jump straight into Delta Lake. Going back to that high-level view, we're using Delta Lake directly in step 1 and 2. For step 1, we're doing a one-off creation of a modeling dataset, which is all just boring SQL. So what I've shown you here is the important part of the syntax, using Delta. This is how you create a Delta table in Databricks. It's super easy. But this is where it gets really cool. Every month we run a scheduled job to update the modeling dataset. But that update doesn't just overwrite the table, it merges changes and retains history using Delta Lake. So let's take a bit of a detour and talk about this Delta Lake thing. As always, the first step when you're trying to figure out why you're supposed to care about a new technology is to go to the website and see how it describes itself. Now I did that for Delta Lake and saw heaps of things that look really important to data engineers, but I just didn't care about them at all. From a data science point of view, this is all fake news. From our point of view, Delta Lake gives you versioned tables for reproducible data science. I'm going to repeat that again for emphasis. For data scientists, you care about Delta Lake because it gives you versioned tables for reproducible data science. I'll show you a quick example of how versions work. These two queries have exactly the same count star query, exactly the same table, but you can see I'm selecting different versions of the table. And you can see that when I select the two different versions, the two different tables have different row counts. I think that's pretty cool. I was pretty excited when I found out how this worked. So how do you make changes to a table so that these versions get created? It's pretty easy, and it looks a little bit like a join. The main difference is, of course, that you're using this merge into syntax, and all of the join conditions go at the top. Then, down the bottom, you've just got this update logic. So you've got a when matched and a when not matched. So this is updating matched rows and inserting non-matched rows. It's also pretty easy to do row removal where there's no match, but I didn't need to remove any rows. My data set is never going to need rows removed, so I didn't show that here. In this example as well, I've created a temporary view, which I haven't shown, and that temporary view has all of the latest data, so that I use this update query to update the table on the disk so that it matches the temporary view, and it creates a new version. Every time this runs, it creates a new version of the table. So of course, you can query the history to find out what versions exist for your table, so you can do programming around these versions. And you can also use timestamps instead of version numbers. So if you want to skip straight to answering how did this table look on this date, you can do that using the timestamp syntax. I think that's pretty cool, really. So we're going to come back to the pipeline now. With Delta, we create a new version every time this job runs. The latest version is always the most accurate version, and we can recover any previous version of the training data set. I think this is a pretty big win for reproducibility, because I can easily recover the training data used to train any of my models, and it only took a few magic words in a few SQL queries to make all of this work. So I think that's a pretty good success. Let's move on to MLflow tracking. We're going to have a look at this model training step, the first purple one there. I don't have time to go into the code where I'm training the model, but it's pretty straightforward. If you want to see how it all works in detail, you just need to check out my full talk at the Spark and AI Summit in June. Essentially, it's written in R using Facebook's Profit. It trains a model for every ticket grouping, so think of it like a ticket queue, for example, and it stores the model and metadata in MLflow. It takes an argument for forecast date, which allows backfilling, and that defaults to the month end. So if you call it without arguments, it just goes and does the most recent complete month, and it will train a forecast up to that date. But you can also provide a historical date, and we can train a forecast for a given date in the past. And I'll show you more about how that works later. So once again, we're going to take a bit of a detour and talk about MLflow now. So once again, we're going to take a look at the website for MLflow and see how they describe themselves. In this case, it's a bit more targeted at the data science audience, and it's clear that there are 4 different things going on here. I don't have time to dig into all of these, except to say that I really like the fact that MLflow lets you just use the bits you need. In my case, I got a heap of value from the tracking components. That's what I've used, and that's what I'm going to dig into today. If you'll allow me a little bit of narrative license, I'm going to magically skip over a whole bunch of stuff, because this is the pot of gold at the end of the rainbow. And this should hopefully make the rest of the section make more sense. This is my objective. This is the thing that I wanted to get to. I'm using MLflow as a database for models. So this is the primary key in my database. Every forecast that I generate has a region, has a date, which is the latest day that was included in the training data, has a ticket grouping, a support ticket grouping, and has a platform. We're a company that has cloud and server products, so it has a platform as well. That's my unique key for the forecast. And it's obviously unique to our business, but hopefully the concept makes sense. I've also got this batch number in here. Now, it's a bit of a hack. It's sort of part model versioning, part state management. Effectively, the scoring notebook always uses the latest batch, which lets me do backfill, as you'll see later. But it also means that if I run the training notebook followed by the scoring notebook, I don't need to pass any state data between those 2 notebooks. The scoring one will always take the latest batch number. And this is really cool. For every model, I can track the table and the Databricks Delta version, which means that I can recover the exact training data set used for every single model in MLflow. Now, this is a huge win for reproducibility, but even more useful is the fact that it makes it possible to debug when something goes wrong and a new forecast looks odd. I can just go back to the training data set and back to the code and see if I can reproduce that strange behavior. We're also keeping the model itself in MLflow, but I did this using native R. I just dumped it out as a binary file in RDS format and added it manually as an artifact. MLflow actually has some really cool tooling around this for Python, which would have let me do this without writing out to a file. But given I was in R and the tooling isn't quite as mature there, I just rolled my own and it worked quite easily. Obviously, there's a heap more I could do here as well. Like in particular, I should probably generate a bunch of diagnostic plots and I should store them here as well, but I just never got around to it. And just to prove it, here's a genuine extract from my task list where you can see I really did plan to generate and store the diagnostic plots. And maybe one day I'll get around to doing it. If you haven't seen how MLflow logging works, it's pretty easy. All of the examples online are in Python, so I'm going to stick with R here and show you something a little bit different. Essentially, within your training loop, you need to tell MLflow when you're starting a run and then when you finish the run. And in between those 2 API calls, you can send parameters, you can send metrics, which I haven't shown here, and you can send artifacts to MLflow. And it will add those to the database like I showed you before. It's pretty easy to do here in R, and it's even easier in Python thanks to context managers. One thing that might not be obvious is understanding where your experiment lives. You can see here I've used a hard-coded experiment ID, and it's worth exploring where that came from. So in this case, I've attached the experiment directly to my notebook. Every notebook in Databricks has an experiment attached to it, sort of like hidden or secret. You can just click Runs at the top of your notebook, and then click the link that's shown here. This will bring you to the MLflow tracking page for your notebook. The experiment ID is right here at the top, and if you just log your experiment runs to MLflow without specifying an experiment ID, this is where they're going to end up. In my example, I did specify the ID, but that was just for flexibility so that I could change it later if I wanted to. And this is what my actual experiment looks like. There are many hundreds of MLflow runs in here, probably in the thousands by now, and you can inspect them all interactively if that's your thing. It's good to be able to debug this stuff in a browser, I find. And because it's attached to my notebook, I can also see them here in the right rail. Well, that's not particularly useful at this scale, but it is good to know that they're there, and if you're using MLflow at a slightly smaller scale or for a more traditional experiment, it's pretty handy to have your runs there in the right rail. So now let's take another look at this overview. I added a few more layers so we can talk about how state's being transferred. You can see that I'm using Delta to transfer state between the first 3 steps. Then I'm using MLflow to transfer state from the model training to the model scoring step, using that batch number that I showed you before. Now this isn't bulletproof. I'm opening myself up to all sorts of bugs, mainly due to race conditions. But I've plugged those gaps by locking down permissions and preventing other people from writing to my tables, which it's not perfect, but it's been pretty solid since the 6 months or so that it's been running. And just finally, we use Delta to write the scores out at the end as well, so that we can get the history and see what the model was predicting in the past. So now we're going to take a look at that final scoring step in more detail. First, it reads from MLflow. So it does 2 passes. It reads all of the models in from MLflow and it filters for the ones that it wants, the ones with the latest batch number, and then it does a second pass to recover all of the parameters. And then from that, it goes and builds an execution plan, which is basically a for loop. It stores each forecast and prepares aggregates for consumption. So it's like it goes and runs the model forward and stores that data in a table in Spark. And then once it's got all of them together, aggregated together, all of the different lookbacks and aggregations that we want to do, it appends and overwrites the results into our data lake. So we're using Delta for that. We're keeping a new version every time we overwrite the results in the data lake. And finally, every single row that we output in this final scoring table has a URL that links back to the MLflow experiment that is the exact model that was used to generate that row. So we'll talk about that a little bit later, but I think that's pretty cool. Now, reading from MLflow is super easy. As you'd expect, it's quite similar to writing into MLflow. I'm not going to dwell on this, it's all in the documentation. What does matter though is the output. So I'm using Databricks Delta again here, like I said, to upload the results from R into a temporary table in Spark, and then to update the output table so that it reflects the forecast from the latest model run. I've broken this out into 2 steps here, just to be absolutely certain that if the scoring job gets rerun at any point, it always wipes the previous scores for the latest forecasting date, and then writes them again. In fact, the whole pipeline is set up like this. Any individual step can be run or rerun as many times as I like, and it won't ever break anything. Again, this is just to make debugging easier. If I can run the same script 10 times in a row, it means that I can debug it. So let's talk about how all of these runs are scheduled. I'm really going to make sure that I get my value for money from this meme. But really, we're going to talk about notebook workflows specifically as they're being used in this pipeline. So it's not really a detour. This is where it all starts. This is a single scheduled job which runs once per month. That notebook, that first scheduled notebook, then uses the API to run each of the sub-notebooks in order. I do this as a single-threaded process so that it helps me avoid those race conditions I talked about before. Although speaking of race conditions, there was actually a bug in the MLflow R package which was causing my jobs to fail occasionally. So you can see here what I've done is I've wrapped all of my jobs in this run with retry function, which automatically retries the job 10 times in the event of a failure. So it's still single-threaded, which means that it retries the job over and over and over until it succeeds, and then it moves on to the next job. And as for why they all say success at the bottom, that's because you can actually return a success string from a notebook. So you can see here that all of my notebooks return the string success if they make it all the way to the end. And if they don't make it all the way to the end, then they return a failure code. So you can see here how that run with retry function is defined in Python, and it uses those return error codes. If it returns an error, Python catches the error and then goes and reruns it. I think I modified this from something I found on Google, so I can't claim any credit for this very clever piece of code, but it definitely made huge improvements to the overall reliability of my pipeline. We haven't actually seen a single pipeline failure since we started using this, even though some of the individual tasks have failed occasionally due to that MLflow bug that I talked about before. And you can see here how it works in practice. The failed run and the internal errors are preserved for debugging after the fact. In fact, if I click into that failed job, I can see exactly where that job failed and I can see why it failed. But then a second brand new job is spawned automatically, and that second job completes successfully without intervention. You can see at the bottom, it's returned that success code. And regardless of whether a run succeeds or fails, the output from all of the runs are preserved, which means I can use print debugging all over the place and just leave it there in production, because those logs are preserved along with their context. You can see the code that generated them. You can throw tables up. Anything that you want to do as part of debugging in future, you can just leave it in the notebook. It's really handy for this sort of work. The other thing you might have noticed is that I'm using widgets as notebook arguments. This lets me pass in either an auto string, which my notebook resolves to the last day of the previous month, or a specific forecasting date, which allows me to do backfilling really easily. This is how it works when it's scheduled to run every month. We pass the argument auto, and it goes and picks, like I said, the last day of the previous month, and builds a forecast using all of the data up to that date. But it also means that we can run really large backfill jobs just by passing in specific days in the past we want a forecast to run up until those days. So in essence, we can produce the forecasts that this pipeline would have produced based on what it knew back at that point in time. And that allows us to do offline analysis to determine whether the pipeline is generating useful forecasts and whether the pipeline is generating stable forecasts. So let's take a quick review of how this pipeline works and what we've managed to achieve. Let's take a step back and look at this from the point of view of someone who's just started in the team and has been tasked with taking ownership of the pipeline, which isn't really a hypothetical because I've actually moved on to a new role now and someone else had to take over my pipeline. So this hypothetical person named Jeff can see from the scheduler that the pipeline is calling 3 notebooks in order. And then they can look inside those 3 notebooks, because it's Databricks, you can just click into it. You can look inside those notebooks and you can see that state is being passed between them using Delta tables and MLflow. In many ways, using notebooks like this has the effect of being somewhat self-documenting. And even more so if you use the markdown cells in those notebooks to explain what's going on. This is the first page they're going to see. And when you click down into that task at the very top, or into the runs at the bottom, it guides the reader towards everything they need to know. As far as pipeline handovers go, I think this is pretty good at being self-documenting. And from the user's perspective as well, the consumer of those forecasts who's just looking at the table, it's actually pretty easy to discover the pipeline as you need to, because every row in the forecast has a URL, which then guides the user towards the MLflow record for the model that generated that row. The MLflow record gives you a link to the notebook in the pipeline, as well as access to the model binary and the table name and version, which in turn actually gives you access to the version dataset used to train the model. So in the end, it's not just reproducible, it's also inherently discoverable, which is a real asset for those downstream consumers, especially those undeclared consumers who stumble across your tables and use them without ever speaking to you. You can't fix everything, but you can give them the tools that they need to seek you out when they have a problem. And you can see here what that looks like. If someone was to stumble across this table, it's immediately clear where to go if you have questions about where this data came from. And so once again, I'm never ashamed to reuse a meme, but I think this pipeline has been a great success. We've been running it for 6 months now without any human intervention, and it's been producing high quality forecasts every month. And if we hear anything that suggests the pipeline is starting to drift in the future, it's a pretty painless process to extend our usage of MLflow and to start tracking model performance metrics, or to start adding new debugging plots, or whatever we need to do. And I think that's the key takeaway from this talk. If every project looks like a full-blown engineering project from the start, it's really hard for businesses to take a risk on new initiatives. So by empowering data scientists to explore and build and deploy their own complex solutions using a managed platform, I was able to quickly build a forecasting pipeline that was good enough for the needs of the business without engaging any external engineering help. And then as my needs become more complex and as I need to build in more functionality, the platform can grow with me. And I think that's pretty cool. So that's it from me today. It's the middle of the night in Sydney right now, so I can't be with you for a live Q&A, but I'll be sure to check out the recording and catch up on the discussion. Thank you for your time.